Welcome to Sci-tech Cocktail, where science and technology collide to reveal the wonders of the universe. Today we go back to the very first moment of time, the beginning of everything.
Before galaxies, before atoms, before time and space even existed, there was a moment. Not a minute, not a second, just the tiniest sliver of time imaginable, something we call Planck time. That's about 1,000,000 trillion trillionths of a second. In this moment, the Planck Epoch, the universe was hotter and denser than anything we can replicate or truly imagine. The laws of physics, the ones we rely on to understand everything around us, they didn't apply yet. No matter, no light, no space, just raw, unimaginable energy. And then, the universe began to expand. That's where our story begins.
The moment the universe began marks the start of what we refer to as the quantum epoch, also known as the Planck Epoch. This briefest sliver of time stretches from exactly t equals 0 to about million trillion trillionths of a second. That's a decimal point followed by 42 zeros and then a 1. This tiny moment is so small, it's named after the father of quantum theory, Max Planck. And that number, 10 to the minus 43 seconds, isn't just random. It's called Planck time. Below this scale, time and space may lose all meaning. Our current physics simply doesn't work there. In this era, all four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces are believed to have been merged into a single, unified force. No separate rules, just one indistinguishable interaction governing everything. There were no atoms, no particles, not even light. Space didn't stretch in any meaningful direction. And time didn't flow like we experience it. The universe was a single, infinitely dense point, what we call a singularity. But even that word, singularity, is a placeholder. It's the edge of what our equations can describe. At this point, our two best theories, general relativity, which explains gravity and large-scale structure, and quantum mechanics, which governs the tiniest particles, simply don't agree. That's why the quantum epoch is still a mystery. We don't have a full theory of quantum gravity yet. Until we do, the Planck epoch remains a frontier we can't fully cross. But we do know this, everything. Space, time, matter, and energy began here. This wasn't just a moment in time. This was the beginning of time itself. In the very first sliver of time, far less than a blink, the universe wasn't just hot, it was beyond imagination. Temperature soared to nearly 100 million trillion degrees, far hotter than anything our minds can truly grasp. And the energy? Off the scale, around 10 billion trillion electron volts. That's about a trillion times more powerful than anything we've ever achieved, even inside the world's most advanced particle colliders, like CERN's Large Hadron Collider. In that moment, there were no atoms, no protons or neutrons, not even the quarks that make them, and no photons, no light. The universe existed as something stranger than anything we can truly picture, a state known as quantum foam. It was a wild, chaotic sea of energy, bubbling, surging, collapsing, where space and time had no clear meaning, and everything fluctuated through a unified quantum field. Here, virtual particles flickered into being and vanished instantly. Energy fields flared violently, driven by the bizarre rules of quantum mechanics. Some theories suggest even microscopic black holes may have appeared, born from these tiny fluctuations, only to evaporate almost immediately. In this earliest age, space and time were anything but stable. They twisted, trembled, and constantly reshape themselves, warped by relentless quantum turmoil. Imagine space not as a smooth fabric, but as a stormy ocean, writhing and crashing at scales smaller than anything we can detect. This was the raw birth of reality as we know it.
So, if this moment, this extraordinary genesis of everything, was so profoundly important, why can't we observe it directly? Why does it remain shrouded in an impenetrable veil of mystery?
Imagine, in that unimaginably brief flicker of time, the entire observable universe was smaller than the size of a single atom, even tinier than a proton. This momentous event, the very genesis of our cosmos, occurred a staggering 13.8 billion years ago.
No telescope.
No matter how powerful dot can ever penetrate that veil of time to glimpse an object so infinitesimally small, occurring in such extreme conditions. Light from that primordial moment simply cannot reach us, nor could any instrument resolve such a microscopic origin. The very earliest universe remains hidden from direct observation. Our only avenue, then, is to attempt to recreate those conditions here on Earth. To conjure the colossal energies present in the early universe, we require a particle accelerator, a monumental machine capable of smashing subatomic particles together with such force that, for a fleeting instant, it exquisitely mimics the intense environment of the universe's birth. The quest lies in replicating an environment that existed at energies close to an astounding 10 to the power 19 gigaelectronvolts. Particle accelerators are our only tools for this. They launch tiny particles, protons or electrons, to nearly the speed of light, then hurl them into head-on collisions. When these particles impact at such immense velocities, their kinetic energy transforms into raw, concentrated power, briefly forging the extreme conditions of the early universe. It is our closest approximation to a mini Big Bang. At those staggering energy levels, matter as we know it simply melts away, and the fundamental forces that govern the universe become unified, just as they were at the dawn of time. By meticulously studying the aftermath of these unimaginably powerful impacts, physicists hope to glimpse the very fabric of reality as it existed in that first, fleeting instant. However, achieving that specific 10 to the power 19 gigaelectronvolt environment of the Planck Epoch pushes the very boundaries of our current understanding and technological capability. It would require a technological advancement far beyond our wildest dreams, the kind of engineering only an intergalactic species might command. We would need to construct an accelerator spanning trillions and trillions of kilometers in circumference, a machine quite literally the size of our entire Milky Way galaxy, which stretches some 100,000 light-years across.